Okay, so I'm very happy to introduce Dr. Andrew Feeney, who's a lecturer in ultrasonics within the James Watt School of Engineering at the University of Glasgow. He obtained his PhD in 2014 from the University of Glasgow before undertaking 2 years of postdoctoral research in subsea ultrasonic technology. He was then a research fellow at the University of Warwick from 2016 to 2020, developing new ultrasonic sensors for measurement in environments of elevated pressure and temperature towards 200 bar and 500 degrees C respectively. Okay, over to you then, Andrew.
Thank you very much. Hi everyone. So today I'm going to be talking about my experience of some material science challenges for a new generation of adaptable ultrasonic devices. So my primary specialism is in ultrasonics. I do have an overlapping experience of material science as well, with predominantly experimental experience. So what I'm going to do is just highlight some problems or challenges that I've encountered over my short career so far, and I'll be happy to take some questions at the end as well once I'm finished. In general, ultrasonic devices are widespread across medicine and industry for a wide range of applications. These include non-destructive and destructive processes. Those which are non-destructive include those such as metering, flow measurement, inspection, proximity measurement. For example, in car parking systems, your average car nowadays might have 8 ultrasonic sensors inside, which are configured with the system to beep if you're getting too close to an obstacle. And non-destructive also includes flaw detection, materials and manufacturing, including online processes now. Inspection of materials as they're being fabricated is a very valuable and important process, including for safety critical systems. Destructive ultrasonic processes include surgery, welding, food processing, cleaning, drilling. These might be in geological manufacturing processes as well. Very, very recently, a new generation of ultrasonic technologies has started to emerge. It's very much the cutting edge, no pun intended, of ultrasonics at the moment. Well, ultrasonics is can be considered as a relatively niche field, but actually, because it covers so much of technology, it's surprisingly applicable to many different areas, and there's a lot of vibrant research activity going on. So what I'm going to present today is based on my own limited experience, and doesn't mean to I can't fully comment on all of the aspects of ultrasonic science going on at the moment, which is really exciting. Ultrasonic devices are now being designed for operation in ever more hostile environments and to display multifunctional and adaptable properties. So here I'm going to discuss some of the challenges, especially with respect to material science, but also with respect to how we design, fabricate and operate ultrasonic devices, and those technologies which might be coming in the near future as a result of our endeavours and our transition to advanced ultrasonic technology. So as a brief overview of my research career, and Phil has provided a little bit of this already, but for the past 6 years, up until May of this year, I have been working in different areas of predominantly industrial ultrasonic technology, both at the Glasgow University and at the University of Warwick. Wrapped within this, I did also do some work into ultrasonic surgical devices. I'm going to cover a little bit of that today. But for the last 10 years, my primary specialism has been in ultrasonics. And I've done a little bit of numerical modelling and finite element analysis, but predominantly I do focus on experimental results, which makes the current climate a bit more challenging for my research. I've engaged with a number of different industries throughout my career. I've been very fortunate to do that. These are just some. In my PhD, my PhD wasn't tied to any particular company, but I did some maybe more impactful outreach style activities alongside, and tried to incorporate some of what I did in my PhD into that. As an RA at Glasgow between 2014 and 2016, I was part funded by Oil and Gas Innovation Centre to look at the subsea ultrasonic technology. And that was a really kind of exciting, interesting project to be a part of. And when I moved to University of Warwick, I was part of a broader industrial network. I was a research fellow on an advanced EPSRC Advanced Fellowship with a number of different project partners, not all of which are listed here, but these were my primary interested parties. So I have built up a good relationship with a lot of these companies now, which is very good. So the first question is why adaptable ultrasonic devices? So, I mean, as I said before, this is all in the context of my own work. So I predominantly work with low ultrasonic frequency sensors and actuators, and that means that they're designed for operation from around about 20 kilohertz to 100 kilohertz. They're widespread and diverse applications, but the sensors and actuators for these applications still tend to be designed to operate with optimum efficiency in one vibration mode. So, for example, an ultrasonic device used for orthopedic surgery will be designed to operate at a precise frequency, to operate on the tissue for whatever is intended. In order to do this, these devices tend to involve very careful control of geometry and material properties to precisely tune these parameters. And these parameters include resonance frequency, amplitude, and there is often very little room for error, and that can it can often limit application performance. Even with advanced precision manufacturing, ultrasonic devices can still lie outside their performance requirements. So if you look at, for example, the image on the right-hand side there, these are very quick experimental measurements I took of 5 nominally identical ultrasonic transducers, which are commercially sold and used in car parking sensor systems. And they're all the minima there are supposed to be on 40 kilohertz, but you can see the divergence there, the discrepancy between even 5 nominally identical devices. So it's a real challenge for manufacturing to even be pairing up, for example, sensors you might want to use in together, to propagate ultrasound and receive with another. You'd want to maybe have them the same. So these challenges in ultrasonics are very much interrelated with the materials behind them. So, why adaptable? So we maybe want multifunctionality. We want to maybe get more out of a single device that we have at our disposal. We might want to tune performance. So related to what I've shown you in the figure on the right-hand side there, if we can maybe tune the performance to something that we're operating in. Multiple resonances. So an ultrasonic resonator, which at the moment will resonate at one frequency, we might want to use that for something that's slightly different. So is there a way we can design something where we can very, very expediently and rapidly change that resonance? Remote repair. So maybe we have a device that's in an environment that's not easy to access, or is dangerous, or is impractical. So maybe we want to be able to repair these devices in some way without having to take them apart or replace any part of it. Mitigation of inevitable inconsistencies. So there are always inconsistencies when you fabricate something that's complex. That's what I've encountered anyway. And that does relate slightly to tuning of performance. But if we can find a way that these differences between devices and these inconsistencies can be mitigated, then that would be a very good thing. And the final one there that I'm going to show is application in diverse environments. So maybe you want to have a device that, for example, in flow measurement, it might be suited to operation in a single phase fluid, or like water, but then maybe you want to take measurement in something that's a bit more complex than that, a fluid with particles, wastewater systems. So there are all sorts of these possibilities that I think we can tap into by a materials and dynamics approach together from different perspectives. And in terms of what I do, I think that I do complement a lot of the researchers that I'm now working alongside at Glasgow, and if we can harness a lot of these collaborations and expertise together, then I think a lot of the areas that I'm outlining here and work that I'm doing now would really benefit from that. So my general investigative approach is looking at smart phase transform materials, many of which are rarely used in ultrasonic devices, and there are reasons for this. And it's not really just because they are impractical or nobody's interested in them. It's just that they tend to be quite difficult to use. So when I say phase smart and phase transforming materials, I mean materials like shape memory materials, those whose properties can be switched in response to some sort of external stimulus, or can be trained to respond to an external stimulus. I do appreciate in ultrasonic devices, and those who already know ultrasonic devices well, I appreciate that piezoelectric materials, magnetostrictives are commonplace, and they are technically smart materials. But when I say smart and phase transforming materials here, I mean those materials rarely used, like shape memory materials, which I'll discuss a bit more detail. New transducer concepts. So I'm looking at different ways of adapting popular configurations of transducer we use now, some of which haven't really changed much in many, many years. And for good reason. They're reliable, high performance. If it's not broken, you don't need to fix it necessarily. But there are ways that we can adapt what devices we have now to make them ready for our new generation of ultrasonic device. And performance analysis in application environments. So we need to be deploying these devices in a broader range of applications to really test their limits and test what we can do. So here I'm going to discuss some common configurations of ultrasonic device, some recent research activity associated with each, and not just my research, but generally a general indication of maybe what's out there. I'll look at key materials challenges, which I'll highlight as I go through, and where I intend to add to the general research landscape, and where I maybe need collaboration. So that's something that I'm hoping will kind of develop and evolve through this. It's a particularly challenging time at the moment, but I'm hoping over the next few months, just some things can be started, which would be really beneficial, I think. So, common ultrasonic device configurations. So, shown here, one is a Langevin, and one is a Flextensional or bending actuator. Now, the Langevin is like what I've mentioned. It's a concept and a general configuration that hasn't changed that much for many, many years, but it's widely used. And both of these are very common, but for different applications. The Langevin is more a general purpose device that would be used for surgery, cleaning, The flextensional bending actuators, in their conventional sense, they were originally built predominantly for sonar, and they're still used widely in various sonar applications. Other devices which are popular include piezoelectric micromachined ultrasonic transducer and capacitively micromachined ultrasonic transducer. These are technically also bending structures. So really I do kind of class devices that I've worked with as either kind of a Langevin stack formation or flextensional bending. My experience really is with the piezoelectric based devices of both types. Magnetorestrictive materials is another common driver choice. For example, some of you might be aware of magnetorestrictive patch transducers, and these are popular in like non-destructive ultrasonic testing, waveguides and pipes and plates. You get ferroelectrets, which are like thin polymer films, which exhibit piezoelectric and pyroelectric properties. Electromagnetic devices are also popular, so driving through electromagnetism, especially for non-destructive testing. The field in general is massive, and it's very difficult to cover everything. We also get devices which are, depending on the composition and the physical properties of the piezoelectric, you might have a clamp-on bulk shear wave piezoelectric devices for non-destructive testing. So there are different types, and my primary experience has been in piezoelectric, and many variations of flextensional devices especially exist. In a Langevin transducer such as we see here, we might expect materials, for example, to be in the order of, for example, the back mass might be a stainless steel, the front mass might be titanium, so you can build these from relatively conventional materials. Now, the Langevin transducer, just as a brief introduction of this. So, most of you will probably have heard of Paul Langevin. He invented the hydrophone to detect objects using sonar, such as submarines, icebergs. The general construction of this is not too dissimilar to the Langevin style of transducer we have now. The fundamental configuration is a stack of ceramics, like we see here. So this is a transducer I built a few years ago for the subsea ultrasonic technology project, and it's sandwiched between front and back masses. So this whole transducer is tuned to operate at a specific frequency and a specific mode of vibration. So this transducer here was designed using finite element analysis, and that at about 20 kilohertz will operate in a longitudinal motion, so it will vibrate in a longitudinal mode. The advantages of a Langevin-based transducer include high electromechanical efficiency, stable output, relatively low energy consumption, durable. But a lot of these properties come from the fact that we can use this type of piezoelectric ceramic. So lead zirconate titanate is PZT, and that's by far the most popular, based on its favorable, shall we say, properties at high amplitudes and high cyclic motion. For a transducer such as this, you also need to make various calculations, and when you're constructing it, that you maybe wouldn't necessarily need to calculate for your modeling. So when I put this together, I calculated from first principles the optimum pre-stress for the ceramics, for example. And when I put it together, I found it worked really, really well. And you can see at the bottom there, the approximate length of this transducer is 200 millimeters. Some of these devices are much larger than that, but some are much smaller. And I've been working to miniaturize some of these designs as well. So practical applications. So I've covered a couple of these already, but we have, for example, enhanced oil recovery from porous rocks. enhanced strength mechanical components. So there's evidence that if we impart ultrasonic vibrations into a compressive compaction process, that we can create enhanced strength parts, and that has been used in the manufacturing industries before. Industrial cleaning, I'm sure a lot of you will already know about industrial cleaning with ultrasonics. Metal forming and welding, a lot of the research at Glasgow in previous years is focused on this. Food processing, so if you use a stack transducer with a cutting blade on the end and vibrate at specific frequencies, we can precisely cut food materials with very little sticking of the food to the blade, much more efficient and clean than before, with much less kind of waste for the food manufacturer. We have drilling and exploration. So in a kind of related application, Dr. Patrick Hartness does a lot of work into this in CMU at the moment, the Centre for Medical and Industrial Ultrasonics. And another primary focus of CMU is ultrasonic surgery, and they are very, very experienced at how Langevin-style transducers can be used for surgery. Now, flextensional bending transducers, these now shown here is basically a generic list of flextensionals that have been popular for many, many years. Now, the predominant use has been in sonar, and much research is now looking at how these can be adapted and miniaturized. And, you know, there are 7 principal classes. I thought this was a really nice figure, and I took it from my textbook, which is referenced at the bottom there. And there are, you know, key features of each that are highlighted. Much of those devices there in common use would be very large, very requiring quite a lot of energy to drive. But my research has been looking at, if you see in the center there where it says class 4 and class 5, I've been trying to miniaturize these 2 types of transducers and use them for different applications. And that's where some of my research is going to be going in the future as well. So some practical applications of these. So you can see many for underwater hydrophone use. The top right figure there shows a modified version of a class 5, which is used for providing high amplitude ultrasonic vibrations for actuator operations, not just limited to underwater use. There's a nice application in the bottom right there, which is showing transdermal drug delivery, which I think is very really interesting. The way that works is that the elements are all configured together to provide an ultrasonic signal, ultrasonic vibrations, which changes the permeability of the skin, allowing the transdermal delivery of drugs such as insulin. And then at the bottom there, you have a bit of work that I was involved with, which is surgical cutting using a modified transducer. Now, some more recent activity in flextensional devices. So 4 images there are taken from papers that have just been published, and well, published in the last few months. And you know, there is a lot of research activity out there. I've just taken 4, but I mean there are plenty other papers out there and plenty of other evidence of study. But current research still does focus predominantly either on sonar or on energy harvesting applications. So in the previous slide, there was also an image of a concept for an energy harvester, and there still is focus on this. I'm trying to look at applications which are building out from that, but it still shows that there's a lot of ways to go now, even now, in terms of building devices which will exhibit multiple optimum or high performance parameters, such as, you know, operating at maybe a low frequency, broad bandwidth, but with a high power output. It just depends what you want for each application. That's one of the reasons for me that I'd like to be able to test the devices that I'm building in different applications to really see where we can go with that. So what I'm going to do now is go through some of my recent research results, some maybe not so recent, but in terms of my career, and look at concepts that I have been working on and want to continue investigating. And some of this is ongoing research and some part of future plans. So 3 examples are a tunable frequency class 5. Other examples are remotely repairable class 4s and 5s. And then another one is an efficient multi-mode flexural sensor. So a flexural is not really limited to one of those classes, but it's another bending type of transducer. So the adapted class 5 device. So this was the focus of my early research. Now, nitinol is an alloy of nickel and titanium, and it's a shape memory material. And it exhibits 2 major microstructures with different physical properties and a third intermediate phase, which we call the R phase. The change in these microstructures, for example, through modest changes in temperature, and they can be very modest, in the order of only a few degrees Celsius, permits property changes in the material. And one of these is elastic modulus, for example. Now, changing this elastic modulus causes a change in device resonance. And this is achievable in the order of thousands of hertz, which is ideal for an ultrasonic transducer if I want to make it adaptable. Now, a form of class 5 is shown here, which is the cymbal. And the nitinol and different forms of nitinol have been used to fabricate the caps. And these caps vibrate up and down. The approximate device size here is in the order of about 12 millimeters, so you can get an idea of the general size. As well as property changes, nitinol itself exhibits 2 key performances. One is superelasticity, and this is a reversible response to high deformation applied to it. And the other is the shape memory effect, which would be, in my mind, the basis of a self or remote repair concept. So the shape memory effect is actually demonstrated on the right-hand side there. It would have been better with a video, I think, but these are snapshots taken from a video I took in the lab. And sub-figure 1 just shows a looped nitinol wire specimen. I then activate a current, and that current starts to change the microstructure of the wire, and it tries to recover its original configuration. That's what's happening in number 2. And then in number 3, after it's transformed, it's now reached its original configuration. And that's the underlying concept of using something like the shape memory effect. Now, the physical properties affect the transformation temperatures of a material such as nitinol. So does the composition of the material and how the material is fabricated. Now, why would we necessarily want a device like this to exhibit tunability between 2 frequencies? Well, different frequencies, for example, might be very useful for efficient operation in a surgical process, for example, between hard and soft tissues. So if you're penetrating soft tissue first and then bone, the resonant frequencies, the operating frequencies for efficient cutting processes can actually be quite different. And it's been shown in the literature. Softer tissues, for example, typically benefit from a higher operating frequency for cutting compared to those for hard tissue. So that would be one immediate example that I could think of. So in the work that I've done so far in the fabrication and operation of these devices, I've undertaken, various forms of material characterization One of the most successful so far has been using differential scanning colorimetry. So that really is just creating a map of the heat flow against temperature, and using this you can identify where the material will transform. So the DSC result here is shown for nitinol. On the right hand side, the impedance spectra there are shown for a transducer at 2 different phases. So the A plot is shown for, the blue plot is shown for a transducer which is in the lower temperature phase. So this would be martensitic microstructure. And the red plot indicated by B is shown for the nitinol cap in a higher temperature austenitic state. And you can see that we're getting a resonance frequency difference of about 4 kilohertz. Now, what I want to highlight to you here is that the temperatures there are pretty big in terms of what we're showing in terms of the 0 to 100 degrees Celsius scale. Now, that temperature difference is actually achievable over a much narrower temperature window. That just happened to be the temperature I made the measurement at. But you can transform, you can shift the resonant frequency at a temperature difference much smaller than that, just really where the transition is, and that's where it's dependent. I had identified issues with DSC. Residual stresses can cause accuracy problems. So residual stresses in the nitinol itself can cause accuracy problems for DSC and nitinol. And this was particularly evident for superelastic nitinol. Now, superelastic nitinol is where the final transition to austenite is above, just above room temperature. And so it wouldn't be, that would mean that in the context of this DSC plot, that would mean this spike between 70 to 90 would be shifted much lower down, around about 20 to 30 degrees Celsius. And that's where they tend to be for the superelastic material. Now, that kind of information can be found in the paper referenced. There's a lot of work that I still need to do into the superelastic work. But this example really is provided here to show how DSC could be used to correlate with resonant response control of a transducer. If you notice quickly the 2 modes, there's one for each cap, and these change differently. Now, that could be due to different temperature distribution, physical geometry, properties of the cap, bonding mechanism, or maybe something else. Devices in general don't have to be constructed using 2 caps. I could use one, and I have done in the kind of orthopedic device concept. So shown here as well are amplitude responses that I measured for both end caps, both caps on the transducer. Now, in the superelastic regime, on the right-hand side, I actually see ripples in the responses, and there's clearly something happening at the microstructural level that I need to study further. But it was a really interesting result. The transducer was operational, but we just see these ripples that I didn't see when I was looking at a different composition of nitinol, which is on the left. The accuracy of DSC may well extend to other types of SMA, or the inaccuracy rather. It might affect an SMA such as copper, zinc, aluminium. That's another shape memory material that's commonly used. And the other thing to consider here at the moment is that fatigue is also a concern for ultrasonic devices, and that's another criteria, another performance that I've not investigated into too much detail at the moment, but I'd really like to. Although there are studies existing showing that this can be improved by tailoring composition and the fabrication processes. But as a broad summary for the Class 5 device, key material challenges are accuracy of DSC, but also other measurement, material characterization and measurement processes. The influence of superelasticity is not well understood. The effect of fabrication of shape memory materials into more complex configurations needs to be done. because at the moment I've just been focusing on the cap. We need much more progress in modelling and simulation, and we need to have a better understanding of how transformation temperatures are influenced by various manufacturing processes, and also how bond layers affect performance. So how we physically bond the device together and how that affects how the transducer works. The next part of my work looked at adapting class 4 and 5 designs for fabricating surgical devices. Now, conventional surgical devices tend to be limited by resonance requirement, so that affects Langevin transducers in particular. So that's why I moved to be using Flextensional based. So for a Langevin stack transducer, every part of it has to be precisely tuned, whereas with a Flextensional, we're able to attach a cutting insert onto the top without precisely tuning it to the resonance of the device, just purely because it's operating in a flextensional motion. So the vibration of that membrane, for example, in the picture you can see in the center, that's just a completely different operating mechanism to a stack transducer. So part of the work that I want to do now is making these much more adaptable, intelligent, you know, maybe produce you know, cutting inserts which are more remotely repairable, for example. So that's part of what I'm going to be, what I am working on now and studying. The example here is for orthopedics, but it's an adaptation of a class 5 cymbal transducer. Another transducer that I did was an adaptation of a class 4 design, and this is an ultrasonic biopsy needle. And I did this in partnership with a company, OnScale, and they're experts in multiphysics modeling and simulation. The bottom left shows the ultrasonic transducer that I built. That's the rough size of that is in the order of probably 5 centimeters across, perhaps, lengthways. And that's the concept there that I fabricated. I looked at 2 different coupling methods. So what I mean by that is how the vibration and the oscillation of the piezoelectric material translates to the vibration and operational performance of the device. So one method was by using epoxy resin to sandwich everything together, and the other method was using interference coupling. So designing the caps to clamp on to the piezoelectric bar with like an interference fit almost. The mechanical coupling between the piezoelectric and the cap is clearly a limiting factor for device performance. 2 results there at the bottom. The key thing to notice there is that using interference coupling, we're able to obtain a sharper response. But if you were driving that transducer harder, the chances of there being some sort of dislodging of the cap is greater. And so there are a whole number of challenges associated with this type of device that we need to rectify. So there's mechanical coupling. You know, how do we really introduce the phase transforming materials such as nitinol? Looking at how the device behaves under certain operating conditions, and then again fatigue performance, which is another thing to consider. The next part of my research that I wanted to briefly cover is looking at the Langevin-type devices for operation in hostile environments. This really relates to the subsea work that I did for 2 years at Glasgow, just after my PhD. I looked at, with industry, I looked at a system where compaction and compression of granular geological materials was necessary, but also transducers for withstanding or operating in high pressure and high temperature environments. So the results there show some of the materials characterization methods that I employed. The design, one of the designs that I came up with is there in showing it being trialed in Norway at my industry partner. and I've got some sample data on the right hand side showing how the amplitude of vibration makes quite a difference to the compressive performance, the compaction performance in the geological materials. And so being able to adapt how the device is working to make it more effective, depending on what material you're working on, makes a big difference. In terms of, especially in terms of operation in high temperatures, there are limitations, and those limitations predominantly refer to the piezoelectric materials. It should be said that I'm not yet an expert in ceramics. I'm just more aware of the challenges, and a good recent paper, I think is a good recent paper, is actually shown at the bottom there, for anyone who is interested. Materials challenges include, current and target environments for my research can reach hundreds of degrees Celsius, but some popular piezoelectric materials with their favoured properties aren't really suitable for those environments. And Curie temperatures are often very low. High temperatures can affect in general the structures of and the dynamics of structures, including if a component material changes size or shape in any way, it will affect the resonant performance. There might be phase transitions triggered in piezoelectric materials, might be depoling, degradation, chemical degradation of ceramics, structural defect propagation might cause thermal instabilities, and there also, just include the materials challenges that I've already discussed. So there are many, many different challenges for operating devices in hostile high temperature environments. Ceramics themselves tend to be designated as soft or hard. So, soft or hard means it really indicates the mobility of the dipoles or domains, and the depolarization behavior. So for actuators, soft piezos with low polarity are commonly used, but then you might have harder piezoelectric ceramics which are used for high power applications. There's been interest in lead-free materials, not just from a safety point of view, but lead-free means that you could operate these piezo materials at higher temperatures. The problem with that is the amplitudes that we can achieve are a lot lower, so we need a bit of a balance there. So there might be a case to make for lead light, but there's definitely progress that we can make. The final part of research that I want to discuss in terms of future adaptable devices is the high frequency flexural. And that's a device that I've been working on for the last few years at Warwick. So the flexural transducer has been fermented more laterally in car parking sensor systems, and it's a relatively straightforward composition, as you can see there. Another type of bending transducer, but not quite. This is of a circular edge clamp disc. It really has, the technology itself really hasn't changed that much until 2016, when we started to do a lot more research into it. My goal overall is to create efficient multi-mode sensors for hostile environments in multiple fluids, but also for optimum performance in different modes. So we can make them multi-mode already, just operating with efficiency is a bit harder. Why would you want these to work multi-mode? Well, for example, in flow measurement, higher frequencies might be desirable to reduce interference of system noise with a center frequency, and these noise might come from components inside flow structures such as valves. So being able to tune these devices would be really good, and it, we'd also perhaps be able to obtain higher resolution and so all of these aspects are really important. I've looked at some different ways of manufacturing these transducers. Caps are currently tend to be kind of machined as a single part, but I looked at some laser welding of a membrane and sidewall together, as can be shown on the left, just as a new way of fabricating them. Because the problem with current devices is that there is an imprecision at the interface between the membrane and the sidewall, and even slight rounding there can really badly affect dynamic performance. You can see in the top middle picture, these are measurements I took from one device showing operation at two very different frequencies. Now you can see by the y-axis scale on both of them how what we can get out of operating at that 40 kilohertz mode compared to 176 kilohertz. Now, is there a way we can make, try and balance that a bit? So that's part of what I'd like to look at. And the other aspect of this is looking at how the dynamic performance of these transducers as you put more energy into them. So there is a measurement I took showing a clear softening, so a softening nonlinearity, where the resonant frequency of the device is dropping as the energy going in increases, and that commonly affects piezoelectric transducers. Here is an example of where flexurals are being deployed, so in high pressure environments, and where they're going to be employed more and more in the future. So adaptable forms of the flexural for these environments is important, so they're going to be able to withstand such conditions. So one of the studies that I completed recently was creating a vented form of flexural which exhibited a stable resonance response all the way up to about 100 bar, which you can see in the bottom right image, and that's compared to a classical flexural transducer which had a very unstable resonance performance. I'm looking into different forms of this, but if I'm able to achieve resonance stability in a high pressure environment as well as optimum performance at different modes, that would be and at different frequencies, and that'd be a big step forward. In general, flexural based sensors are going to feature for in situ measurement systems for different industrial applications. So we need to overcome a number of the key challenges associated with these transducers as well. So we need precision fabrication. We need to maybe avoid reliance on epoxy resin again. So the resin is used to bond the ceramic to the cap. We need to have a better understanding of how nonlinearity is affecting device performance. This also comes from material nonlinearities, of course, as well, which I've begun to investigate. We need to look at how resilient the devices are to the high temperatures and pressures, and consider the piezoelectric issues like those encountered by the Langevin-based transducers. And we need to think about how we can avoid, chemical structural degradation in hazardous environments. Now, the good thing about the flexurals is that we're quite free with how we can use different materials for the housing, for the actual cap itself, but all of this needs to be investigated. So, in general, many materials science challenges exist, and these challenges are manifold, and I've covered them already, but a number of common challenges include the fact that many advanced materials haven't yet been properly investigated for ultrasonic devices. The influence of different fabrication methods and performance has to be given further attention. We need to be paying more attention to non-linearity, because when you're using devices in different environments and applications and operating conditions, all of these aspects are important and will all have an influence on the non-linearity. How we drive the devices, so piezoelectric materials is a key challenge. Fatigue is another key challenge. Fatigue performance is critical, and we just don't have as much information about that yet. And just looking in general about how these transducers are performing in situ for hostile environments, pressure, temperature, perhaps radioactivity, many others. So opportunities for collaboration include, predominantly I'd like to look into, as broad areas, multifunctional devices, maybe advanced materials as a concept in itself. I do look at biomimetics to enhance performance of ultrasonic transducers, and if I can bring that in some way, that'd be really good. And just looking at in situ measurement environments for these transducers in a range of hostile and complex media. So I'd like to thank everyone for their attention, and I'd be happy to answer any questions.